We will learn about symmetric matrix in this particular class. A square matrix definition is written over here. Square matrix A equal to Aij is called symmetric matrix. IFF if and only if Aij is equal to Aji for all I and j, and A transpose is equal to A. Now let us have a look at this definition and let us try to fit the definition with an example so that it becomes very convenient to understand. Okay, so have a look over here. Have a look at this matrix. Okay, the elements are A, H, G, H, B, F, G, F, C. Okay, now this particular element corresponds to A11, this particular element corresponds to A12, this particular element corresponds to A13, this particular element corresponds to A21, this particular element corresponds to A22, this particular element corresponds to A23. Okay, this particular element corresponds to A31, this particular element corresponds to A32, and this particular element corresponds to A33. Now if we interchange I and j, the elements are same. That is what is the meaning of this. So have a look. A12, A21 elements have been interchanged. Okay, so those are same. Okay, A12 and A21 elements have been interchanged. I and j elements means I am sorry to say elements, I want to say subscripts I and j. Okay, they have been interchanged. Okay, so A12, A21, so those two elements must be equal, so those two elements are equal. Okay, A13, A31, 13 and 31, there is an exchange. Okay, A13, A31, so G, G. Okay, those are also same. A32, A23, okay, exchange of I and j, so those two elements should also be same. So F and F. Okay, so those elements are equal, so you can clearly have a look at this symmetric matrix and you can understand easily. Now obviously in such a condition the transpose will be equal to the element itself. Under such a condition the transpose will be equal to the matrix itself, not element. The transpose will be equal to the matrix itself. Okay, now let us have a look at this A matrix and have a look at its first row. This is the first row, this is the first row of this matrix. So if we want to find the transpose, what will happen? The first row will become the first column. So first row became the first column. So let me mark it with green color so that you can understand. First row became the first column, so it became the first column. Now second row is this. Okay, it becomes the second column. Okay, it becomes the second column. So H, B, F. I am interchanging the rows and columns. I am finding the transpose. I am simply finding the transpose. And after taking the transpose, you will realize that both of them are coming out to be the same. Okay, so this is the third row. Now this will become the third column in transpose. Okay, so this is the third column. Okay, now have a look at this matrix once again. Clearly this matrix, even after taking transpose, taking transpose, the matrix has remained unchanged. The matrix has remained unchanged even after taking the transpose. Okay, so this is the property of symmetric matrix. Okay, this is the property of symmetric matrix. So all the elements of symmetric matrix must be real. This is the first condition. So I told you regarding these two conditions. And those conditions were also satisfied. Now have a look at these properties of symmetric matrix. All the elements of symmetric matrix are real, must be real. Okay, if some iota element is there, that is not allowed. Okay, iota is not allowed. The complex number iota in any of the terms is not allowed in a symmetric matrix. Okay, iota term is not allowed in symmetric matrix. That is, all the elements must be real. No complex number is allowed. No complex number is allowed in symmetric matrix. Okay, so this is the thing. All the elements of symmetric matrix are real. In case of symmetric matrix, all the elements and above and below the principal diagonal are same. Now this is the principal diagonal. What does it want to say? This is the principal diagonal. This yellow colored diagonal is the principal diagonal. Now if we have a look at the corresponding elements on both sides of the diagonal, so this and these elements correspond because this is the diagonal. So this element and this element are reflection of each other. this element, if there is a mirror, if there is a mirror at the principal diagonal, assume there is a mirror at the principal diagonal. So this element and this element are mirror image of each other. This element and this element are mirror image of each other. This element and this element are mirror image of each other. Okay. So in case of a symmetric matrix, all the elements above and below the principal diagonal are same. So element above the principal diagonal and below the principal diagonal is same. Element above the principal diagonal and below the principal diagonal is same. Above the principal diagonal element and below the principal diagonal element is same. Okay. This is the thing. Okay. Now when over here there is a mistake in case of all the elements, all the corresponding elements. Okay, we should say all, instead of all the elements, all the corresponding elements. Okay, make a correction while making the notes. Make a correction while making the notes. Okay, over here in case of symmetric matrix, all the corresponding. Okay, put the word corresponding. All the corresponding elements above and below the principal diagonal are same. Okay, so this element corresponds to this, they are same. This element corresponds to this, they are same. This element corresponds to this, they are also same. Okay, this is the thing. Now third property, from the fourth property onwards we will study in the next class. From here onwards we will study in the next class, but over here have a look at this third property of symmetric matrix. Diagonal matrix, scalar matrix, identity matrix are always symmetric matrix. What does it want to say? Okay, so it is saying that diagonal matrix, okay, diagonal matrix, I will explain you this particular fact. Okay, diagonal matrix, scalar matrix. Okay, so now scalar matrix. And what is the third type of matrix? It is saying identity matrix. Okay, it is saying identity matrix. Identity matrix is also called as unit matrix. You are all aware. Okay, let me write identity properly. It is not looking proper. Okay, so these are what? These are always symmetric matrix. What is it saying? These three type of matrices are always symmetric matrices. They are always symmetric. Why are they always symmetric? Have a look. Take an example of diagonal matrix. So I will take such an example that over here, let us take a different example, something which is interesting. Okay, now what is a diagonal matrix? A diagonal matrix is a matrix where only diagonal elements are present, or other elements are zero. Okay. Diagonal matrix is such a matrix where only diagonal elements are present, other elements, non-diagonal elements are zero. So non-diagonal elements are zero, non-diagonal elements are zero, and diagonal elements are non-zero. Diagonal elements are non-zero. Such a matrix is called as a diagonal matrix. Such a matrix is a diagonal matrix. Now, if you have a look at this element corresponds to this element, so they are equal and zero. Okay. This element corresponds to this element, so they are equal and zero. Okay, this element corresponds to this element, so they are equal and zero. And whenever such things happen, it becomes a symmetric matrix. Okay, whenever such things happen, it becomes a symmetric matrix. It becomes a symmetric matrix. Whenever this type of condition is satisfied, that is, corresponding elements above and below the principal diagonal, when they are equal, it is said to be a symmetric matrix. Now let us take an example of scalar matrix. Okay, let us take an example of scalar matrix. So 89, okay, 0, 0, 0, 0, 0, 0. This is an example of scalar matrix. Okay, now this is the principal diagonal. This was principal diagonal over here. This will be the principal diagonal, obviously. Okay, now all the elements above and below the principal diagonal, let us have a look. This element corresponds to this, both of them are 0 and equal. Okay, now this element corresponds to this element, so they are also equal. Okay, and they are both 0, obviously. Okay, this element This element corresponds to this element, this yellow element corresponds to this yellow element, so both of them are also same. Okay, so this is also a symmetric matrix clearly, because when we okay, one thing I forgot to mention, if you take its transpose then it will be same, because it came out to be symmetric matrix. So if you take its transpose, it will be the same matrix. Okay, over here also, if you take this matrices transpose, if you take this matrices transpose, it will also be the same, it will be the same as this. Okay, so scalar matrix is also symmetric matrix, scalar matrix is also symmetric matrix. What about identity matrix? Similar logic. Identity matrix, what is example of identity matrix? 1 1 1 0 0 0 0 0 0. This is an example of identity matrix. This is an example of identity matrix. You can certainly check the things. Okay, all the elements, corresponding elements above and below the principal diagonal, corresponding element above and below the principal diagonal are equal. This is the principal diagonal. Okay, so this will also be a symmetric matrix. So it is saying that a diagonal matrix, a scalar matrix, and an identity matrix, they are always symmetric matrix. So this fact you must remember. Okay, from here onwards we will study in the next class. From this fourth property onwards we will study in the next class. Thank you very much.